I'm going to go ahead and share the screen, and we'll have their presentation up, and they'll just give their chat on the chassis design.
Do you want questions at the beginning or throughout? Or sorry, at the end or throughout?
The way we have this presentation set up is at the end. But if you have something like really pressing, I guess, what do you guys like? You guys all right with that, or would rather have it at the end?
Oh, Adam's here. Hey, what's up, Adam?
I'll take my questions till the end. Oh, hey, Adam.
So I just got home, so I'm going to try to eat my dinner as quietly as possible, but if I'm be on mute.
No problem. Yeah, no pressure at all. All right, cool. So let's do this. And whoa, trippy. All right. Here we go. All right.
How loud do we have to talk?
Swafford, take it away. No conversation. Can you guys hear us okay?
Yep, loud and clear.
Cool. All right.
Okay, well, this is the chassis design review. We have made some progress, so that's wonderful. All right, so the goals of the chassis are to haven't changed. We're going to build a rules compliant formula style chassis. We want our center of gravity basically as low as possible and as central as possible in the car. We want to make it an easy car to work on, so ease of access to our battery, motor, suspension, all the stuff in the car, and we want to keep the weight under 90 pounds, which I believe all these goals are easily attainable, and I think we've achieved pretty much most of them. Okay, so objectives, high strength. So between these also haven't changed since our last review. So using some type of steel, 1020, 1040, or any of the 4100 series. Triangulation at critical points, high torsional rigidity, low CG again, lightweight, all stuff like that. Here is the most recent chassis right now. This is from the soft design review. All of our dimensions here are in millimeters. And I have the angle on the front row hoop just from the vertical. That's just the look that we have those updated support bars for the front roll hoop that you told us about the last meeting. But I think other than that, most of the stuff hasn't changed. Here we go from the top. This is just to show basically the width of the car of each section. All right. All right, Zach, take it away.
Okay, so our next part was to perform some tests to verify that our chassis was going to be structurally sound. And we did this with a static load analysis for frontal impact, and we also did a torsion. We were planning on doing a dynamic simulation, but we couldn't get it quite figured out. So we just stuck with the static load, and we were pretty confident that our results were going to be good enough because we were compliant with all the rules. Yeah, like I said, all the simulations were done in SolidWorks. For the frontal impact, we fixed the rearmost part of the chassis, and we subjected the front of it to a 20G load, and the results of that were good. There was no yielding. There was no extensive deformation. Everything looked pretty good. For the torsional test, we fixed the rear suspension points, and then we created a set of mock arms for the front suspension, and we subjected, I think it was 200 newtons up on one side and down on the other side to simulate rolling of the chassis, and we did not get any extensive deformation on that. With some research, we found results from other teams, and we were on par with that. Here's a graph of the, I think, yeah, this is the 2G. We don't have the picture of the 20G, but it was pretty similar to this. We got, I think it was a ½ inch of deformation on the 20G impact, which was good because it didn't yield. Here's the torsional rigidity. You can see how it's fixed in the back with those green arrows, and then the loads in the front. This is displacement. It displaces the most at the suspension points, which is where it should displace. And here's just another front view of the torsional test, and this is in degrees of rotation about the center axis.
Yeah, more for a stiffness value on that, we got about, I think it was 1.9 kilonewtons per degree for the front stiffness of the car. What?
And the deformation seen in the front impact is without the impact attenuator?
Yeah, it's without the impact attenuator. So, actually, I think that is. Okay, so yeah, things that we know are not rules compliant right now. We kind of discovered these over the past 2 weeks since the soft design. Our shoulder harness bar needs to either be relocated or it needs support bars added, because currently it is on the main supports for the main hoop, and it can't be there without extra support bars. We really have to wait on a seat for this because we need to be able to locate it basically below or in line with the driver's shoulders, and we're not exactly 100% sure where they're sitting yet. The other thing, so we need accumulator protection design that needs to get done, and we're pretty sure that shouldn't be too hard to do. The tractor system protection needs to be designed. Once both of those electrical systems are really we have a geometry for them, I believe that would be pretty easy to get those done. We need to do a static tilt test. We haven't done that of the chassis yet, just as itself. It helped to have the projected weight of the car, but those items still have to be figured out. But it would be nice to have an initial sort of guess at if we're going to be able to pass that 60-degree tilt test. And then the other item is that our chassis right now just barely fits the 95th percentile male. And we are all three of us that are working on the chassis are pretty much on a 100% agreement that the car needs to be made bigger, just to fit them better. It's not a drastic change. It's probably about 3 inches longer, 3 inches wider in the very front bulkhead to actually fit your legs with the steering wheel shaft, and then about 3 inches taller so that the driver has more clearance between the helmet and the main roll hoop.
This is our chassis with the impact attenuator. The right image shows it needs to be updated, but we need two cross
Single cross.
or single. It can be either single or a double. Probably go with single, since our edge width is over 26 millimeters. I think that's what the rules compliance said. But also with this, we can do another frontal impact, but we'll see less yielding, since with the impact attenuator on there than without it.
Yeah. And this is just the standard impact attenuator.
Yeah, we got it off the FSAE website. Standard bolt holes that they recommended. So everything should be to general specifications on that.
For manufacturing, we're looking at getting our steel donated from State Steel. This will be A513 Type 5, which is about a 1026. It'll be DOM, so it'll be mechanical tubing, so all the dimensions will be accurate. We're looking at getting these laser cut as hopefully a donation or a discount from some local manufacturer. We have potential manufacturers right now, but we need to get confirmations after we get the total list of steel that we need and get everything confirmed. We will most likely bend these in-house. The chassis will also be welded in the house, and the impact attenuator plate will all be purchased, and we'll put all that together in-house. Here's a list of our tubing requirements right now. These are the bare minimum. So we're gonna be looking at getting at least 1.5 to maybe 2 times as much as this. So we have a trial and error, and plus there's gonna be cutoff lengths for when these tube gets cut. So we're gonna need some more for sure. Right now the chassis weighs 55.3 pounds. So this is quite a bit under our 90-pound goal, which is a good thing.
So this is, again, we touched on this a little bit earlier, our future design work, static tilt test analysis. Our current ideas with this is just a hand calculation, simple statics calculation. Our accumulator protection, structural stiffening, that'll be based off our simulation results. See where we can possibly put extra bars in to stiffen up the chassis. Attractive system component protection, the seat selection. I think we have a sponsor for that, so we're looking at seats from their website. Rules review, make sure everything's within code, and then a PVC mock-up so we can see what we're working with as in space, and everyone else can have a general good idea of how much space they have for their designs.
Yep, the PVC mock-up is really going to be helpful for us three, since we've never designed a chassis before. You know, we're just looking at this in CAD on Creo, you know, without actually being able to see it, be around it, measure it, potentially be able to sit in it. You know, we'll know if certain things are working and what's not. And I think that could be really helpful to us before, you know, we get the steel and cut it and weld it. When it's, you know, when it's pretty much set in stone, we can have a cheap way to mock the car up. I think that's it. All right, we're open for questions.
Good, I have a bunch.
Awesome.
Okay, I gotta go back to the, so when you were presenting on your requirements, AKA your goals, to me, that outlines very much customer requirements. That's what you want to achieve. Have you thought about assigning target values to each of these goals so that you know if you meet or do not meet your target?
I believe I have that on a different paper. Hang on just a second. I think actually, no, I think that's what the objectives. So the goals just really outline what we want the car to be. And the objectives say like how we're gonna do that and if we meet it. I don't know if we have any more specific, you know, sort of goal meeting sort of requirements, expectations, or whatever for that.
So let's look at number 3, low CG near main roll hoop. How do you know if you've achieved your low CG? Is 5 inches low? Is 10 inches low? Is 0 low? So it would help to assign a target. That way you know if you're meeting your goal or not.
They're also a little bit limited in assessing their center of gravity for particularly the battery. We haven't given them exact dimensions or where we have them. They just haven't been factored into any of the CAD or the events. So
The other thing is that the chassis is a lot lighter than we thought it was going to be at 55 pounds. The battery is going to easily be double that. And so that's really going to be what affects where the CG on the car is more than the chassis itself. So that, the low CG was just to give us an idea of how to put members around the car. We never assigned a target value for it. It was more of a qualitative, like what looks good.
I get that. So one of the things I would urge you to do is, from a team perspective, what does that CG need to be in order to meet the tilt test with a feeling of being comfortable going into that tilt test? Because I know you mentioned that you were going to do some static calculations.
Yeah.
You should get a value that says if our CG is below this, we're safe for the 60-degree tilt test. And that would be your engineer requirement.
Yeah.
And for example, on number 2, you gave me a torsional rigidity value. Do you know if that meets your rigidity target or not? based on this? What was your
Yes.
objective?
So we were just aiming for what the value that I'd seen online was, if you're near 25 kilograms and 2 kilonewtons per degree, you have a pretty competitive, it's a pretty stiff chassis, and 55 pounds is right at 25 kilograms, and 1.9 kilonewtons is right at that threshold of 2 kilonewtons per degree. So I think we've just about met it. I mean, that's why we still have the goal of adding some maybe non-structural stiffening members around the suspension mounting points, just to give it that extra boost. The other thing is we do still want to do a torsional rigidity test on the rear suspension of the car. We did it in the front, but we also want to measure the rear. I'm pretty confident that the rear is going to be a lot stiffer than the front, just because of the distances with the suspension arms back there are a lot shorter, and also just there's a lot more heavy members in the rear than the front.
Yep. So my point just being was it's really important for the team to set measurable objectives. That's how you know if you met your goal or not at the end of the day when you go to competition, and can talk about that to design judges and so forth. So just think about that moving forward. My next question was, do you have a dimension from the top of the main hoop to your main hoop bracing?
I do not know it offhand. I'm pretty sure. I think the dimension it has to meet is like 6 inches, and I'm pretty sure we're well within that. I can tell you for certain in just a moment.
Okay. Yeah, no big deal. I just wanted to make sure you had that rule in mind.
I did note that that is a requirement within the rules folder.
Okay. And then additionally, what the angle of that brace is also a rule.
Yep. I know that's within the 30-degree limit. And I know when Greg came to me last month for the redesign, we wanted to move that vertical bar. Let's see if the mouse comes up here. Yes. This vertical bar right here, we wanted to move it forward. I know we kept an eye on what this angle between the vertical and that was, and it's still over the 30.
Okay.
Yeah, over the 30 degrees. So.
So for your front hoop, I see you have it at a 10-degree angle to the front.
Yeah.
How during the welding process are you going to ensure that it is no more than 80 degrees? Because that could become a rules issue if you go too far in one direction.
Yeah.
So do you have a plan for that?
Measure.
That was Zach's answer, was measure.
So how will you handle if the heat due to the welding starts to warp things in directions you aren't familiar with? Do you have a die, or are you using some sort of fixture?
You just tack it up and watch your heat control.
Yeah.
Just want you to be cautious because you're skirting that angle rule. Just bringing it up as a concern.
Yeah. Okay.
Do you have your side impact structure dimension here? And is it 2 rules based on your desired ride height?
Yeah, I think they're right. So this is off just like the ground. So the ground being the very bottom of the chassis that was just sitting off the ground. It's 325 millimeters. It has to be between 300 and 350. And I know Greg said that the chassis already sits pretty high. I think, what is it?
Yeah.
2 or 4 inches. It's 4 inches. So we should be absolutely fine.
Well, if it sits 4 inches higher, you're going to be way over the 350.
Yeah. So we could bring it down. That's definitely okay. I'll make that note.
Another detail I thought of while we're talking about manufacturing is, do we have to consider residual stresses due to putting the frame into place?
Um,
Because they'll be different than the perfectly unloaded
yeah,
that we've been doing in the model.
that's true. I'm not recalling at the moment if that is actually going to be
Might be negligible.
It should be negligible, or it's actually gonna help us more than hurt us, if I remember correctly from, material science. As long as we don't, I don't know, drop the, overload it basically. Cause then it will be catastrophic. So that would be the only worry there, is would be a fatigue failure. Which this car shouldn't see enough use to have a fatigue issue. And that can be something that we can look at. We can do a fatigue analysis. That's could do that. I don't think we thought about doing, because we've scratched doing any dynamic testing because it's proven to be far more difficult than we first imagined it would be. And the fact that we can't validate it with any real world results until we build the chassis, it's pretty much not worth to do as far as time goes with design and other things that need to get done.
We have time for any specimen testing?
Okay.
Or putting that into do we have to get that for the SES at all, or?
No, for the SES, we just have to tell them what material we're using.
Yeah.
Basically, yeah, and provide every single image we can with annotations and measurements and everything. Yeah.
Okay, I'm gonna keep going with my questions because I know we're already past our 20-minute timeline. I got a lot of them. Do you have the templates that you need to meet for this chassis modeled in CAD so that you can drop them in there and check?
Yep, I have them. I have the 95th percentile modeled. I have the cockpit opening, and I have the model for the the front hoop to the pedals, that very front bulkhead. Yeah, I have those all modeled.
Okay.
I know for absolute certainty that the cockpit one fits. I haven't tested. I don't think we haven't tested the front bulkhead one. We haven't tested it in an assembly, but we did make the all of the piping of the front bulkhead. We sized them all like I can't remember. It was 10. I think it was 10 millimeters on each side over to count for the width of the pipes. Yeah, we can do that pretty soon. But I'm confident that will fit.
Okay, as long as you're checking those. What is your method for attaching the front bulkhead to the frame? Are you using screws to do that, or are you welding it directly to the frame?
So are you talking about the plate or
The plate? Yep.
The plate. That is going to be welded.
Yeah, so there should be tabs. We haven't put those in yet.
Got it.
That the bolt holes will go through, and then we'll have, since you have to have two methods, I think we'll epoxy the
structural epoxy. Yeah.
Yep, the attenuator onto that plate.
Okay.
And then the plate is welded onto the chassis.
Sounds good. Okay, my next question is, have you looked at how many tubes you have coming together at any specific nodes, and looked at the stack ups and how you'll handle those angles all coming together during the welding process?
It has been a concern that we have looked at. I know it's been a reason for us losing some tubes. But from what our loader, Zach, has said is that this is manufacturable. So,
okay.
I guess if he has any comments to make on that, Zach?
The one main concern I had is that we find somebody who can laser cut these tubes so we can get perfect copes on them, so we don't have to do it by hand. So we have to do them by hand. It'll at least double our time of manufacturing this.
Yep.
Just get everything.
Yeah, we use the company VR3, and they're like one of the best for cutting tubes, and we still had issues with 4 or more tubes coming together in a node. So I just wanted to put that out there as a potential manufacturing concern.
Yeah, the main concern is like the front one near the impact attenuator, where there's like 4 coming together. Yeah, right there. That's probably the worst spot, I would say.
I would be more worried about where your side impact structure comes up because the angles are more drastic. That's where, when I was doing this, I found more issue with the gap at those larger, longer angles than the smaller ones that you're pointing to up at the.
Okay.
And just to
So
give
just keep it in mind.
some short background, Zach is a very, I'd say, accomplished welder. What was it? state champion?
Oh, I competed in high school and.
Where are you using chromoly then?
Budget, I would think.
Okay. If you can get it donated, use chromoly. That would be awesome. You could weld it.
It was taken.
Okay. So are you guys in charge, from a chassis perspective of putting any tubes in for the headrest, or is a different team taking care of that?
We are most likely going to be in charge of that. We did not realize how much of an issue not having a seat picked out was going to be until about 3 weeks ago. So we've been working with, the sponsor that we found is, I think, Sears Manufacturing. So we have a potential seat sponsor. I've looked at several of their seats. 2 of them look like they would work fine because they're very low padding. They're not like what they usually make seats for are like tractors and excavators and things like that. So it's a very massive, bulky seat. So what I think we're going for is to have something that's a pretty minimal seat, so we can fit and really play with the angle, and then we'd make a headrest restraint.
Yep.
We have not looked into that because, as stated, the driver barely fits in the car right now, and we really want to fix that. That's a main concern that we all have right now, and we're very much focused on making sure that. And that's what also, again, the PVC mock-up is going to really help us be like, okay, this is where a person should sit, and this is how they should sit. So.
Yeah. I know a lot of teams, and specifically our team, we use just foam from Home Depot. Glued it together, carved it out. It was light, it was cheap, it fit some drivers didn't need it. So definitely don't put a tractor seat in there. That would weigh you down. You guys talked about the harness bars, so I'll skip my question on how is the shoulder harness and how is the submarine belt going in. Sounds like you have some more work to do on that.
Yeah.
For the impact attenuator, do you have to do any sort of drop test, or because you're using the standard design, are you permitted by rules?
Yeah, so the reason why we chose the standard design is because we have to do no proof on it. We just have to submit a receipt that we have the standard impact attenuator.
Good choice.
Yeah, because it is a lot of testing, and I don't believe we actually have you have to have like all the facilities that meet a certain specification. I don't believe we have that, so I don't.
Okay. Cool. So when you were talking about your steel, where you're getting it from, if your supplier falls through for the donation, how does that impact your budget? Can you afford to buy these tubes on your own?
Yeah, so I had that in there originally. Like, if it wasn't donated, it's under $1,000. Yeah, it's easily under $1,000. The bigger cost would be getting it cut if we can't get that at a discount or donated. But even still, it's not going to be. I don't think it's going to affect the overall compared to the budget for the race car. It's a drop in the bucket.
Okay. My next question is, you mentioned bending in-house. Do you have a bending machine with the proper size dies, and do the bends in your model match those dies?
I do not know. Go ahead.
So I know we have a tube bender, but that's about all I know.
Yeah, we do not.
I don't know anything about dies.
Yeah, what they have. I know I've seen it. I haven't used it. I've used the pipe cutter, which is right next to it.
Okay, just make sure that if you have bends in your model that they match the dies you have, because if you have the wrong size bend, it's going to mess up all of your angles and it's going to put you in a tough position.
That's a very good point.
That's a good point.
Okay, and then I think the PVC mock-up is an excellent idea. We also did that our first year, so I'm glad that you are taking the time to do that. It's very much worth it.
Okay, cool.
And that was my questions for now.
Awesome.
Awesome, that's our presentation.
Cool.
Thank you, David.
We'll go ahead and get suspension pulled up.
Do you have the right presentation?
I should.
Okay. I did not consider.
I didn't either. I did
Go to
not.
that, it's in suspension. Suspension to your left, yeah. Is that
Can you still hear us?
Yeah.
Sorry, Missy had a question for you.
Oh yeah, go ahead.
So, based on what we all just talked about,
We can't hear.
But we can't hear you.
She's basically asking, since there's a lot of logistical work to still be done on the frame to finish, when is your ultimate deadline for your hard final design? When does that have to be done by to keep on the project timeline?
Do you have?
Yeah, so me and Ryan gave this a little bit of thought, and yeah, we originally put out the design deadlines of September 24th and October 8th as like the hard design timelines. We've also talked with electronics. They're kind of on a different story because of the complexity of it, but we kind of figured by at least the beginning of November, if we can get everything together, we'd still technically be on track for if we were a normal team building another chassis, because typically around Thanksgiving and winter break is when a lot of teams will build their chassis and start doing stuff like that. So if we figured if we can stick to a plan and get to something around then we should still be in good shape.
Okay, I just wanted to point out that this is probably the first time any of you have welded these types of materials before at these types of angles. So the actual manufacturing time will probably take you a lot longer than you think. So just make sure you factor all that in when you're giving them their final deadline, because you want to make sure you order these with enough time to get all that done.
And actually, so we started last week making a manufacturing plan. And actually, that for me, that's when it clicked about the what is it called? Oh, Brian's not here. The plans that you were telling me, I forget the name of them. Oh, the critical path. So we're pretty much going to do one of those for our manufacturing plan. We gave a rough outline of it, and so we're going to start filling that in from now on. But for this week, we want to focus on getting all the designs and presentations together.
I love that you just used the word critical path.
I figured you'd like it. Well, yeah, it was still funny because we were just kind of talking over it, and I was like, oh my God, this makes so much sense now, and where you'd want to use something like that. So yeah, we'll definitely be putting that into place.
Awesome. Okay, go ahead.
So yeah, I won't distract any further. Suspension. So Greg and his team, they've done a fantastic job. They also have, oh, my bad. They've also had, this one? Okay. They've also had a senior design team working with them. They've been doing a lot of great work, and I'm sure Greg can tell you the rest of the details.
Okay, so first of all, feel free to stop us anywhere in this presentation and ask questions wherever you want. Let's get started. So our requirements for the suspension were to provide balanced handling between corners and straights, have a balanced car. It's got to be simple to manufacture. It's got to be low cost. It's got to integrate correctly with the chassis, which was basically already designed before we really got into the suspension actually manufacturing and how we would manufacture the suspension. We've got to comply with rules, of course, and the main thing is we want to provide a baseline that we can improve on. We don't expect it to be perfect this time, and it doesn't necessarily have to be, you know, the best performing suspension. It's just got to work for us this year.
So did you provide points to the chassis of where your suspension needs to be mounted?
No, we worked the other way around. Michael got the chassis done really, really fast, like last year, and was just like, here's to see if we can make it work, and we can make it work pretty well, as I'll show you here.
Okay, just one thing. The strength then, are you making the suspension points on nodes, or are they going to be in the middle of bars?
Middle of bars on half of them, and on nodes on half of them.
Okay.
Yeah, I'll show you later on. And I have the like the Creo design up as well. If you want to see that, I can move it around and stuff if you need. I have pictures too at the end.
I'll ask my questions later.
Okay, so we did analysis in Optimum K, the suspension software. The main parameters we looked at were caster, camber, KPI, mechanical trail, scrub radius, and roll center. Basically, we meet our requirements that we found online that people were recommending and what other documents have said. The problem is we don't meet our roll center. Everything else is good. In order to change our roll center, we have to modify the chassis fairly significantly, or our uprights. We had an upright design already, and changing them to make them fit, we're just not sure if that's really worth the time and effort right now. Again, our goal is just to have a car that basically drives, and we figured we could focus more on performance next year. I have a chart here of our values. On the far right is our roll centers, and we definitely don't want them to be negative, which they are in the front, and they're fairly negative. We were shooting for about 30 millimeters positive height, 30 millimeters above the ground. So we're not too far off in the rear, but it's definitely a lot of variation there. So it's really not good on either of those. But everything else, we're within our kind of our limits, and we're pretty close to where we want to be.
I mean, my first question is, do you have a requirement of where you want it to be? You want it to be 30 above ground?
Correct.
Okay.
That's what we found online.
Yeah.
I don't know if that sounds reasonable or not, but
I mean, -2, you're basically at the ground line, which isn't a horrible roll center.
yeah, the front was our main concern.
Yeah.
So, yeah, everything else though is where we want it to be in terms of the research that we did on it and what we could find. So it looks pretty good.
In Optimum K, did you look at your values at max Johnson rebound?
Where?
At Johnson rebound, so the
Yeah,
extent.
we didn't look at either of those.
Okay, so this is just nominal.
Mm-hmm.
Okay.
Continuing on, we had to modify the hubs that we were planning on purchasing, and this made sense because we realized that where we're at now, we probably can't afford to buy these hubs, so we're going to have to do our own and machine them and get that sponsored in order to be able to afford the car. So we basically kind of took a design and modified it so it fits our wheels. We were having an issue with caliper overhang, and you can see now that it's resolved and we don't have that issue anymore. We extended the hub out essentially from where the brake rotor mounts, the piece between that and where the wheel mounts, we extended that out, and that seemed to resolve the issue. We did some finite element on it, which I believe Walker will touch on later, and it seems to be strong enough and will work for us.
Yeah.
Moving
That's
on.
slide. So for the front one, I couldn't find the ANSYS file that I did this on, so I don't know the exact loading condition, but
1700.
It was
1700 Newton meter moment. It was.
Okay, but was there a moment about those?
Yeah.
Those mounts.
So basically, those circular or whatever, they were fixed, and we applied the moment about the shaft, but in reality, be the other way around. But as computationally, it's the same thing.
Essentially, according to our tests, the hubs passed and will be strong enough.
What was your factor of safety?
Ooh, no idea. Because,
It was a full magnitude under yielding.
yeah, I mean, if these are going to be steel, like they're very.
Speak up a little bit so they can.
Yeah.
Yeah,
It's 7. What did we think it was going to be?
think what was going to be
The
factor of safety. Honestly, yeah, we didn't really do that, but our thoughts were the hubs would be made out of steel, which has a very high strength, much higher than 15 megapascals. So
I think factor of safety is usually around 2. So I mean, we can go back in and that can be easily changed, and we can and figure out the new moment. Yeah, 2 or 3. So, but it was a full magnitude under yield strength. So that looked pretty good.
Yeah, I guess my question is if you're at a judge and the judge says, "Hey, what's your factor of safety on these hubs you designed in house?" What would you say?
Yeah.
Just something to think about. You don't have to,
Like 10.
that comes up a lot. Factor of safety is huge.
Yeah.
Okay,
Good stuff. Confidence.
so here are our designs for the uprights. The keys for this that we focused on was obviously they have to be strong enough, but we also wanted them to be fairly simple to machine because we don't know yet if we have to pay for them. We really can't afford to pay for them, so we need to get them sponsored, but it'd just be helpful for them to be easy to machine as well. So we have a pretty simple 2D design for the most part. And yeah, nothing crazy about them, I guess. We tested these again. I'm not sure if we know the
Yeah.
factor of safety on these
this
either.
was like gotten off the internet from other teams that have done this for like a standard braking load. Since that's generally the critical time for a upright is during braking. So yeah, I should probably look at this better, but
Yeah. Our general analysis shows that they're strong enough. I guess we need to go back and maybe look at this a little bit closer.
They need to be trimmed down. Yeah.
Hmm?
could be, but it would be marginal weight savings and
Yeah.
probably not.
Yeah,
worth it.
we were not extremely concerned about weight savings with really any of our designs. We didn't want them to be huge, but at the same time, we just wanted things to work mainly. We figured that's something in the future that we can work on, saving weight. Here's some of our mounting hardware. Basically, we designed some very simple brackets and things to mount the suspension, the control arms to the chassis. We also have the bearing cups that will connect the control arms to the uprights. We couldn't find any bearing cups that are the correct size on the internet for purchase. So as of now, we're going to have to machine these. I don't know if you guys know of anywhere that sells bearing cups. We found them, but they're much bigger than what we're looking for. We're looking for like a 3/4 inch diameter bearing to fit in them. But
We usually made ours in-house to match what bearing we wanted to use.
yeah, yep, that's what our plan is. And,
Are you gonna have a snap ring to hold the bearing in, or is it gonna be held in via a press fit and then seating down on that bottom ledge?
we will be using snap rings.
Okay,
I think that's going to be the best way for us to make it work and not have to worry as much about the tolerances and what will happen to it after we weld them to the control arms.
good choice.
So, yeah. Our shocks, we're going to use the standard Ohlins, like TTX 25. These are fairly expensive. We need to do a lot more work on the spring rates for these, but they have a variety of options available in terms of spring rates. So pretty confident that we're going to be able to make these work. They're quite expensive for us right now, but I feel that it's a pretty good choice and it's something that we can use in the future and that the team will be able to reuse for years in the future. So I think it's worth it to just buy these up front. Our rocker designs in the front, not really ideal for what we were looking for, but it's the geometry that we have to work with because the front roll hoop has bracing bars coming to it that kind of block where we'd ideally like to mount the shocks. I can show you that in our CAD file here if I can see.
So for this, have you determined what the motion ratio is based on your geometry of your rocker arm?
We determined the motion ratios, but we still need to work with like our actual spring rates and the weight of our cars is also basically an unknown to us right now. We have a rough estimate of like 600 pounds, but we need to work on all of that stuff. But we have them set up so that the rockers are modifiable. Like we can modify them fairly easily and adjust those motion ratios, and it won't really change our design. I'll try to show it here. or it won't affect our design too much. So here's our front. And this one is the most concerning. We basically just have the shock mounted to a post coming off of the chassis, and same with the rocker. And it's kind of pivoting in the horizontal plane. We wanted to ideally take the shocks and just mount them perpendicular to the direction that the car is facing. So kind of mount them in the same direction as this bar here, but the two angular bars going up to the front hoop kind of restrict us there and restrict our motion and abilities to get mounting hardware into that area. So we believe that this is the best way to do it right now. I don't know if you guys have any better ideas, but this is
Yeah,
what we're looking at doing.
some teams will actually put a bar in between those front two hoop braces that go to the front. So if you put a support there, and then you can mount the shocks up, but then it makes your car really tall. So if you're looking at packaging any aero bodywork that's sleek, it gets in the way of that sometimes.
Yeah, we'll look into that and see if we can make that work. I don't know how we would, I'm not exactly sure how we would get two shocks in this area, in the triangular area there, because it's pretty thin. We'll look into it, see if we can make it work, because ideally it would be nice if everything was kind of straight and simple.
Yeah, is there a reason those bars have to come to the center of the roll hoop? Because if you move them out from each other, not coming together at one node, then you have more room in between for your shocks and springs.
I was under the impression that they had to be there. I don't know if they can move out to the side.
I'm pretty sure they could move out to the side. I don't think they can move a ton though, because of the height difference between that upper upper side impact structure and the top of the hoop. If they move out too much, like down to a node that we could use, they might not be in regulation. So that'd be something I'd have to look into.
As long as they're 2 inches from the top of the front hoop to the brace, then you're set. It doesn't have to match to another node where you're coming in.
Yeah, I'm not sure if that'll make a I guess I'm not sure if that'll make a substantial change. To be able to put a bar between, that is something that we could definitely look into for Greg if he wishes to pursue that.
What are your thoughts on the current design? Do you think it's the smartest way to go? Like, use this option. Do you think it would even work?
Yeah, I think it'll work. I would just like to see your motion ratio calculations and to see if your rocker is going to allow you the travel you need based on your spring rate. So I think you still have a little bit of work to finalize that and make sure this design works.
Yeah, definitely. Yeah, I guess I can show you the rear while I'm up here as well. That's our rear. It's much simpler. Again, we can adjust the ratios of those pretty easily, and I'm pretty confident the rear should work. It's pretty basic. I'll go back to the presentation.
So how much travel do these designs give you to work with in terms of jounce and rebound?
I'm not sure exactly, to be honest.
Okay, yeah, I just didn't know when you would be at your full travel, just to make sure that you're thinking to make sure that you have enough jounce and rebound to, number one, meet the rules, and number two, meet the goals of the vehicle.
Yeah, we need to work on all of that. Our main goal right now is just to see if we can even get a geometry on the car. So, yeah, we've got work to do.
Just for future, one thing that's really helpful is to put your suspension in a full jounce position, full rebound position, and a nominal position. That way the team can see everywhere that'll be and make sure it works in every extreme position and the nominal.
Okay. Yeah, definitely. Where's this presentation at, David?
So go to the Chrome tab. Yeah. There you go. Then, oh, sorry, minimize this. Or no, the,
VMware.
yeah, minimize the VM.
There we
Yeah,
go.
there you go. Okay, now go to the front.
Sweet, okay. So yeah, that was that. I'll let Sebastian talk about his pedal design.
I'm Sebastian. We put together a accelerator pedal and a brake pedal. And since it's an electric car, we're looking at pretty much a mock-up pedal at first, and that was provided by CVS Technologies. They make pedals. And essentially our accelerator pedal is, so the CVS pedal comes plastic from factory, and we made our pedal fit into that pedal, but it's metal. So we pretty much just took out the sensor out of the CVS the CVS pedal, and we applied it to our pedal, and it's pretty much just it's a potentiometer, and it's a pedal by wire or by cable. By wire, yeah, by wire. And then we made a brake pedal as well, and that brake pedal is a brake pedal by
Well, it's gonna be attached to the master.
yeah, it's gonna be attached to the master cylinder of the bike, and we're planning on getting these master cylinders from motorcycle. We actually went up to Waterloo to a shop that is donating some motorcycles to us, and as of now, the 2 bikes that they gave us have drum brakes, so we can't really do much with it. But we're trying to get a third one that has a nice master cylinder that we can use, and we're gonna work from there.
Yeah, our plan is to use 2 motorcycle master cylinders for the brakes. So one for the front brakes and one for the rear. And we're gonna have a brake bias adjustment in there, hopefully. Although maybe it's not worth our time, but we think it'll be pretty simple to throw a brake bias adjustment in there and just have it. We don't have the master cylinders yet because again, they're coming off of motorcycles that are being donated to us. But we're hopeful that we can make these designs work with that.
We also threw these pedals through ANSYS, and they could withstand like 100 pounds of force, so they won't break.
Additionally, we weren't sure if there was I'm sure there's places where you can buy pedals. Weren't sure if you guys had any recommendations on any of that stuff. The brake pedal, I'm sure we could find easily. The accelerator pedal, we weren't positive if there was a place where we could find something that kind of fits our size requirements and fits the design requirements that FSAE requires. So I don't know if you guys had any input on companies or anything, but we're planning on just making them ourselves for now.
I actually got a question that's related for Adam, I guess. So the 2 big choices we saw for the actual sensor itself were Hall effect and just a standard potentiometer. Any recommendations there?
I mean, it really kind of, no, they'll both work. I guess in my opinion, especially for things like this where it's not that big of a deal, I guess, is the simplest solution with the fewest amount of short or pitfalls, I guess, is the one I would recommend. So whichever one you're more comfortable with.
Yeah, in terms of if you want a pedal donated, it's not pretty, but there's a company called Curtis. They donated the pedal to us. They might be willing to donate it to you. It uses a simple potentiometer design.
Okay, sweet.
I can pass along the contact info.
Yes, please.
Yes, please. Yeah.
Yeah. So again, I just have more assembly pictures here. I have a cost analysis here. Our cost is way high from what we want. Fortunately, we have to buy quite a few of these things on here, such as the wheels, are one of them, wheels, tires. We're probably gonna go ahead and buy the shocks from Olin's, which are another large cost there. We're gonna try to get the hubs machined for us. We really need to in terms of our budget. So that will save us some money. The other thing that's expensive is our front wheel bearings, or well, both wheel bearings, front and rear, both sets of bearings are really expensive. So we're looking at finding different manufacturers and people that might sponsor us, because essentially with our budget or with our cost analysis right now, we're not going to be able to afford to build this suspension. And honestly, it should be a lot cheaper than we've predicted. It should be cheaper than 10 grand to do this. So
Yeah.
we got a lot of work to do in terms of just trying to find cheaper alternatives, but we know what parts we need, and have links to everything. So
A couple of questions. So you're only budgeting for 4 springs. Are you gonna stick with a spring rate and go with it no matter what? Or are you gonna buy different ones so that you can swap in and out based on how it feels during the ride?
ideally, we would have different ones, and have multiple options, but just to start off, we're gonna buy 4 and then go from there. See how much money we have, basically.
Okay. And
Ideally,
then,
yeah.
oh, sorry to interrupt.
No, go ahead.
My next question was, I was gonna ask earlier, for the bearings, you're press fitting them into the hub. What tolerance are you holding on those?
What
Those
tolerance?
openings in the hub?
Somewhere. But
I don't know if Walker knows off the top of his head, but he did some research into that and figured it out to find a tolerance that would work, I guess. I don't know. Do you know it off the top of your head?
The ones on the CAD model should be fine.
You know what they were?
Calculated, no.
He doesn't know what they are off the top of his head, but he looked
Okay.
into them and made sure that they would work for us. So
Okay, just really double check that, because if that's off, then you're gonna have bearing issues and
yeah, we don't want that.
before. So just be really careful and cautious and triple check that.
Okay, perfect. Anything else? I think this was it. Yeah.
I'm all set. I don't know if Adam or Missy had any questions.
So the only thing I have 2 things I want to I briefly touch on. For your hubs, just be mindful of tool clearances. It looks like you're going to try to have some nuts or bolts inside some of those cutouts. And if that's the case, you need to be able to get tools on them. If you can't get a tool on them, having the nuts there is not going to do any good.
Okay.
And then, so are you making your hubs and your uprights out of the same material?
The hubs will be made out of steel, and the uprights will be made out of aluminum, hopefully.
So your uprights, which are made out of the softer material, have a higher stress on them. Did I get that right?
yes.
Yes.
That sounds like a good opportunity for weight savings.
Okay.
Just something to think about. You have the model. Can you just change the material properties? Run the hubs in the model with different material properties and see if you can save some money and save some weight, especially sprung weight, which is even better.
Yeah. All right. Yeah, we can do that. Thank you. Anything else?
Not right now.
All right. Perfect. I guess that's
Cool.
it for suspension.
All right, fantastic stuff. We'll go ahead and move on to the drivetrain on time. We'll do drivetrain. All right. Yeah, so this is the drivetrain. Jacob will probably touch on this in more detail, but just to summarize, we originally picked out the MRX 208 as our motor, and then I kind of went on a bit of a tangent pursuit to try and get a motor for free. So that's kind of put everything on hold for an actual motor that we picked. Now that being said, we do have a couple options, and I don't want to steal Jacob's thunder, but Parker Motors is an option. It's still the MRAX, and I think there's one more that I'm not thinking off the top of my head. But anyway, I'll let Jacob go ahead and take it away. Oh, yes.
All right. So this is the drivetrain. Right now, obviously, we're gonna want the car
to go fast. But since it's our first year and we're kind of learning as we go, we'd like to keep it really simple. We're trying to make the most efficient layout for everything, so it just kind of builds on the simplicity. And one of our goals is to just get that motor set in stone so that we can actually start designing more of it than what we have. So as of right now, our planned differential is an MK2 chain drive from Taylor Race Engineering. We're gonna buy it used from Kettering University with about a runtime of 15 hours on it. It's a torsion style differential, and they said it comes with just about everything. Greg had said that we'll probably need to replace the tripod bearings in it, which hopefully won't run us up too much in cost. And their website for this differential doesn't really say anything except that it weighs 8 pounds. But Kettering's told us that if you contact their customer support, they're pretty helpful in getting anything. So we figured out, once Greg had his suspension in mind, our rear axles for sure will need to be about 17.5 inches. We plan on using sprockets off of the bikes that are donated, as well as chains, and so those will hopefully be places where we can save a little bit of money in all of this. And then here's just an overall schematic of the differential and the 2 letters I'll reference here in a minute. So we have a rough model of how our mount will be for this differential. So the big hole is going to fit into the 2 parts with the A's on them. And then we'll be using tensioning rods to connect the mount to the chassis so that we can also adjust the position slightly if we need to. And then we're still working on this mount to brace the differential in so it doesn't slide out of the sides of it. And then, as I said before, we're still working on the motor. Like David said, we were still considering the MRAX 208, and Parker has agreed to let us have anything for 50% off. So that's also something we're still looking into. We didn't see any regulations as to what it can and can't be. There is the power restriction, which that's just something we can change to if our motor's too big. We're still looking for chain tensioners, which hopefully once we find out the motor, we'll be able to know more and to know what we need from those. And the pump is also something that will depend on the motor. But we, like I have shown here, we kind of have some outlines that are hopefully pretty basic for us. And so we're working with this suspension to make sure that the axles and everything is just as simple as it can be, and kind of whatever works best for them, making everything fit. And then once we get that motor selected and know more about it, we'll work with chassis to find the best mounting points for it to help with anything that may make their lives harder. And then electronics will pretty much make everything else work for us, hopefully. Yeah, I believe that's it. So if you guys have any comments or questions.
Does the motor controller fall under the electronics group, or does that fall under the drivetrain group?
Electronics.
Yeah.
Okay. Well, I will save all those questions for later then. So you're going to want to use you were trying to use the sprockets off the bike. Is that right? Did I hear that correctly?
Yeah, that's kind of our plan right now. We're hoping we'll be able to get that to work.
So I just make sure that ratio works for you. You know, the bike's going to have a transmission with 6 gears or so that it's going to be optimized for. With an electric motor, your gear ratio might need to be completely different. So just make sure you do the math on that before you, you I guess, firm up that decision. Make sure those gear ratios are going to work for you.
Okay.
As far as the div goes, I've worked with Taylor Racing a lot. Yeah, their website's kind of useless, but their customer service is fantastic. And those tripod bearings shouldn't cost you very much.
All right, cool.
Ladies, do you have anything?
Nope.
Okay, cool. So in that case, we'll take it over to electronics. They've been doing a great job. I guess I'll touch on this here while Michael's pulling it up. But I know Mara knows about this, but I attended the battery show back in the beginning of September for 2 days. And while I was there, I was able to talk with about 100 companies and got around like 70 business cards. So I would say that my time was very well spent. But anyway, we have been constantly trying to reach out to all these companies that I got in contact with. Some things that were kind of touched over, Spell and AKG, they said they would be able to help us out with a radiator and a fan. Those are the two that I remember off the top of my head. But yeah, it's just been constantly trying to reach out to everybody that we went in touch with. And yeah, I would say that it was very successful. Definitely learned a lot about what kind of parts are out there and what kind of suppliers there are as well.
Okay. Okay, for design review, we'll stick to the main things that would get us disqualified for tech inspection. So we're focusing mainly on the design parts that we've done for the battery pack, for the shutdown circuits, for the brake system plausibility device, and all of that fun stuff. Adam, if you have any questions at all, feel free to stop me while I'm going through it, and definitely, grill me with questions. If I can't answer something that probably identifies a lack of understanding or knowledge, that is probably best addressed here and now. Okay, so as far as where we're at, we're just now getting everything over into formal documentation for schematics, and we're trying to do these design documents so that when we're doing construction, if we've got a lot more interest, particularly with freshmen in the spring semester, I think things tend to pick up a little bit when you've got a chassis that you're starting to build and you're in the workshop. That way we can, if they're freshmen that have some experience in electronics, we can ideally hand something off, or that people know exactly what a component is meant for. But apart from that, we're piecing together our bill of materials, and we're almost done with our battery pack design, and we're starting to work on our microcontroller. We've got a PIC controller platform that we're working on for the two main microcontrollers that we've got. For the pack itself, this is one of our modules. We've got 8 modules in total. The accumulator segments divvied up into 4 segments, but we've got an 80 series 8 parallel design that would put us at around 288 volts for the nominal and around 320 volts maximum. So we're looking at around 40 to 48 kilowatt for the pack as far as what I can do, given the continuous amperage rating of the 25 Rs that we're looking at is 20 amps. So that's what we've got for power, and compared to other teams, that seems to be roughly what they're running at, maybe a little bit underpowered compared to them, but we're definitely not, even with some of the heavier motors that we'd be looking at, I think that we'll probably be fine unless we have to start cutting down on the pack. As far as the total dimensions for the footprint, it's roughly the size of 4 US letter sheets of paper as far as the footprint, and then about 1 high, although I think we added the height recently for our design. We can get to that. As far as, so this is the overall skeleton as we, okay. We've got rows of 8, and then we've got at the junction points nickel bus bar, and you'll see this in the other design. We've got each cell fused. It's not really here in this CAD file, and then we have final terminals for the packs. We've just got our positive and negative. And for these ones, they're not shown here, but we extend them out a little bit and then bend them over right here, and then we put in a we drill just a hole in there and attach with a nut and bolt our actual wire terminal right there. In this, we've got a bit of an overhang in this plastic cap right here. This actually isn't our full design. You can tell it's actually 6 in parallel, but this actually, as far as the limited CAD experience I've got, this actually highlights it very well. Our design isn't too terribly far away from this. We've got a plastic cap. We elected, given the cost, just to 3D print it. Main thing we'll have to look at is how much filling that we do for the cap end, but let's see, any other design aspects? We've talked a little bit about the accumulator container here, but we've got on our next slide, oh, it's the actual pack. We'll talk about the accumulator container, but while we're talking about the pack, we've got this plastic covering to kind of keep the thing taut, to be able to store it and transport it. And these things actually load one on top of another one, so 2 of them go into a given segment. So if we look at the accumulator segment, each of these battery packs is 20 by 8, or yeah, 20 in series, 8 in parallel, although they put 10. Yeah.
Each module is 10 series 8 parallel.
Yeah. My bad. And then the accumulator segment, yeah, would be 20 because we'll connect them directly, plus and minus, and yeah, minus plus. And to keep these things taut when we load them in, we have nylon bolts that we elected to use here. We've got recessed holes drilled, or I guess added into the 3D printed cab. We wouldn't be drilling them. We just add them into the design and use that to kind of secure it. And then there will be holes at the very end, and I'll show that right here. So these are the 2 different kind of holes that we have. These ones at the end that we've got bolts coming up out of the accumulator container that these things slide onto, and then we have a nut, to come down and fasten it down on top of that. As far as the access point for the voltage, as I said, we have the terminal bus bars come out, bend over, and then we and this is actually past where this hangover is down here. So as far as where you'd actually see this, also there's holes through the top, kind of like they look a little bit like Swiss cheese at the top, so you can put down thermistors. We've got them spaced out roughly every 5th one, every 20, 20% of the pack has to be temperature sensed. We've got to put it directly on the negative ends, or which would coincide technically with the positive ends as well, but it just depends on where we're at what we're designating each thermistor to. We've got our fuses right here. These are 30 amp fuse wire. We unfortunately are going to have to test them and verify, but we do have the equipment right now to be able to do that. We're just going to have to see where what amperage they roughly flow at and document that. I've got a data logging clamp meter to do that with, and look at the burnout time, and hopefully the sample speed's good enough to be able to get something reasonable there, or maybe we can get a camera, worst case scenario, to just double check. But anyway, this shows kind of what we're doing. These are 30 amp fuses. We've got roughly 2 of them. The real fuse is going to be a little bit different, so that's why we've got to measure it with roughly 2 of these. And considering the length here, that the resistance to the wire comes into play there for these kind of things, we'll have to roughly try to match that as well, or try to guarantee that we've got the amperage that we've got by picking resistors when we test it. But we also have, to detect when these fuses blow, we've got a fuse detection board that goes in the long space here. We've got about 40 sensors, or it's just optocouplers that we're putting in parallel for these fuses. So when both of these fuses blow, and I'll show it in just a bit, but we've got the wire attaching right here. As far as the accumulator design that I mentioned earlier, we've got the main pack right here. This actually gives them a little bit more precisely. And then we've got a little top nodule that will come up at the just behind the firewall. And that's going to house mainly the BMS is the big one to consider, in the AIRs. However, given that we might be looking at making the chassis a little bit bigger to try to reduce our center of gravity, we might try to bring those AIRs down with the extra room. The 3 inches can definitely help us there, and we've got a little bit of room that we can shave off from these 1 inch margins that we have right here. So we don't necessarily need to have them 1 inch, but kind of wanted to have enough extra material there. And then we also have to put the temperature board, the microcontroller. It's going to be an Arduino Uno that's just reading the fuse outputs, and I already mentioned the ARs and the primary fuse for the battery pack. And I'll get to that in just a bit. And as I said, it's roughly here. This is a little bit exaggerated, definitely, but we are roughly right with the space allowance that we've been given. It might have to change if there's any additional structural members that you put in. But as far as the battery management system, and I just bring this up, I wanted to point out that we're not doing this on our own. This is given that we are designing our own pack, and the reason for that is just the economics of it. It's around a $3,000 difference from Intergus from what we're looking at for the size that we build. Although that price advantage does evaporate the smaller the pack that we make. But anyway, we were going to just spend the money to go with something that's has a known factor for battery management. The main thing this will be doing, because we're doing sense monitoring ourselves, will just be the voltage monitoring and the load balancing and the charging. So as far as the fuse, and sorry, this is a little bit out of order. This kind of shows you've got the battery tab here connected to the fuse, and the fuse is the only connection between the battery tab and the bus bar. And in parallel, we've got a resistor just to limit the amount of current, and then we've got an optocoupler here. So when it breaks, then the fuse detector, or the parallel fuse detector, becomes the only path of current. And if there was enough EMF to melt the fuse, there's probably enough EMF to drive a wire or drive enough current to light the optocoupler. And for the pack, we just OR them all together, transistor logic, and then we just read the eight different packs that we have with our Arduino, and that allows us to check. The fewer that we have to check here, the quicker the Arduino can cycle through them, and the quicker the response can be to open up the AIRs. Thankfully, the regulations allowed us to make that decision with programmable logic, or it wasn't forbidden to use programmable logic for detecting fuses. They just had to open immediately as far as the wording. Until that changes, that's what we're going with. And the big thing that we saw here was, given that we've got to fuse every battery, price was essential. I was able to find some pretty standard optocouplers for about 5 cents, which brings the cost down to about 50 to 60 bucks just for the optocouplers. And here's a close-up of that schematic. Again, we've got a shared resistor limiting the current through this LED. Going right up to the tab, and then optocoupled, and then we've got a pull-down resistor on the emitter. And so when this goes high, when the base gets saturated, the sample point will actually be here on the emitter, which is shared, and that's what the Arduino is going to read, or what actually gets ORed, and then the Arduino reads the output there. And yeah, this is terribly out of order. It's because we're going into temperature sensing right here. These are the temperature sensors I mentioned. We just got epoxy coated because it's the closest point that the temperature, that the low volt comes directly, as far as like it touches, and the only thing separating is that epoxy coating as far as the insulation between the high volt and the low volt. So we just have to have good enough insulation there. And our main strategy here is just to multiplex, the signals. So pretty standard there. We went with smaller multiplexers, 8, to limit the amount of wait time between chip select changes, to kind of minimize the slew rate effects that we see, although we haven't gotten to testing it quite yet. But that was our kind of overall strategy there. So we went with the Mega to fit on they have 16 analog pins, and so we can, the biggest limitation that we have is the bit resolution as far as accurately figuring out that temperature, but it's been good so far in what we've been testing. And here's the just schematic of that. We've just got, this is one of them, and then there's 16 multiplexers in total, and we just have 8 of them coming up to single mux, and then the Arduino cycling through the chip select lines to get those temperature readings in. The cool thing is, because the Arduino knows, or what chip select got the faulty input, and you can actually store them in memory if you have enough of it, but which temperature sensor is giving you trouble, and so you can service it if you have to. There. 29? Yeah, it should well be done. And for our in general, to handle sensors that go between, or to handle short and open circuit detection for our sensors, for our analog sensors, we just limit the usable voltage range by scaling it down with the voltage divider first, and then we take a summing adder and add in a known DC offset, get it right where we want. So the only time that we should be reading 5 volts or 0 is if there's a short or an open circuit. That should naturally be happening. For the microcontrollers mentioned, we're just starting to code for these, the FSAE 33 EVs. We've got the IMD in. We still have to test with it, but that's what we're going with as far as safety goes. And wanted to cover it before going into the shutdown circuit. We're using another DSPIC 33. Mainly the reason these had very easy CAN implementation, and they were quick enough in a lot of the regards that we were looking for. So that's why we chose these, and super easy to program with the PIC kit on board. For the AIRs, this is we picked out the standard kind of kilovac 200. That kind of standard one, but there's several that we found that will get the job done for us. Our main concern is the price and the coil power that we need to keep the thing closed as far as draining off of the low volt pack that we've got. That's one of the more power hungry components that we have on the low volt side. The pre-charge circuits, when the AR is closed, they go through the pre-charge circuit, just a standard time delay, single pole, double throw. So on one side, it initially goes through a resistor, and after enough time is gone, it passes a, just a not low resistance line. And the overall shutdown circuit, we've actually built this so far. We're basically just taking any of these number of faults that could possibly happen, orienting them together, and then putting a low pass filter on it to get rid of some noise glitch. And we just have to pick the, RC values low enough, which we haven't done yet. But that output, if it goes high and it stays high for long enough, then it gets latched on, and then that gets inverted. And the idea here is that the shutdown control unit has to actively turn the AIRs on, and the inhibit has to be off. So the inhibit, the user has more or less control over the SCU control of it, but if the inhibit is on, there's nothing they can do because the AND will turn off. And this is what drives a MOSFET along the coils to energize, and that in turn, the pre-charge circuit is just downstream from that. The T-cell is another design that we had that might be, prone to rules compliance. Down here we see a cascade of resistors, and this actually kind of went with the suggestion that Adam gave last time. I realized that my previous design, the comparator that I was using for checking the voltage, was off of the low volt side, and so I probably couldn't guarantee galvanic isolation, and the voltages were floating reference to that, so I wasn't sure if they would destroy the internal. So I went with a high volt op amp, and I used an and powered it off the high volt line, just reduced down the power. I'm not really powering it too much and just switching voltages. There's not really a whole lot of loading going on here, so there shouldn't be a whole lot of power draw, but I can revise this. The idea, though, is that I'm supplying with roughly 36 volts to this really inefficient line, but not a whole lot of current's getting drawn from it, and giving it a reference voltage of around 7.5 volts, and then doing a similar kind of divide on the actual high volt, or sensing the high volt line after the AIRs. And if that's high, then, optocoupler, and then I've got that control mirrored on the low volt side, and the low volt's actually what's driving the T-cell, where you've got the red blinking. If this thing is on, then this should be on, this should be off, so the two are inverted. And you've got the red blinking and the blinking controlled through just a simple 555 timer, given the frequency of around 5 to 10 hertz. And then we've got the green light, and we're pretty much at the end now. Our problem areas are we still don't have really good ways of dealing with back EMF. We don't have any plan for regenerative braking at the moment. And while we do have a rough bill of materials, we haven't done proper market research yet to actually get costs down. And our price quotes are a little bit high, given that we're dealing with the the motor controller, and the battery, the BMS, and all the heavy, big price tag components. We're looking at anywhere between 15 to 18,000, which is quite a tough build as well. Of course, we'll make changes and roll with the punches if we can. But I guess if you go through questions, I can answer them in the time that we have left.
Okay, so I know you went through that a little quick, so I'm going to lead this off by, can you send this to me, please?
Yes, absolutely.
And I'll try to get you more feedback. But off the top, so I guess because the motor and the electronics team are technically separated a little bit. Because of I just want to make sure that the motor team is aware of the battery design, because that will drive some motor decisions. You're going to want a battery you're going to want a motor that's optimally performing at about 300 volts, because of how you have the battery designs. That's so just touch on that real quickly. For the battery covers, 3D printed battery covers, are those structural at all, or are they just isolation?
We haven't done any analysis.
Well, I guess what's their intent? Do you want them to?
A little bit of not really structural. Oh, 1 second, I've got feedback. Mostly, the only structural aspect would be clamping down. We're going to have a little bit of adhesive keeping the nickel tabs adhere to the spacers, kind of fix them, rotating in this way, but to keep them kind of down for the most part, it's going to be that residual from the bolts, keeping the pack down. But most of the structural support is going to come from padding around the packs. We didn't talk too much about that. And from the bolts through the accumulator container wall itself. And so there is some structural aspect, but the idea is hopefully it's encaged within enough stuff that that's not the main load bearing structure for the battery packs.
Okay. Are you going to be able to print those as a single piece, or are they going to be an assembly? Or do you know?
Be a single piece?
Correct.
Yeah, it'd be a single piece. They'd just be hollow on the inside. And
Yeah, I mean, it's a fairly large, you said it's about the sheet of paper. That's a pretty big 3D printer. I mean, at the school might have something like that, but I know that your typical hobby 3D printer would not be able to handle that, so.
You know what you could do? You could laser cut some acrylic.
Oh, yeah.
If it's not if it's not like super thick.
The thickest point would be roughly 3/4 of an inch for the holes.
Okay.
So pretty thick on the top.
Yeah, I don't know if you you probably couldn't laser cut it, but you definitely could do that on an end mill, like with acrylic. That would just, I mean, that'd be so much cheaper than 3D printing something like that. It's just so much material.
But that would be 3D printing would cost like about 50.
Yeah.
What would it cost about 50?
Maybe $2.
What, 3D print?
Yeah, 3D print, it wouldn't be that bad.
No,
I guess
okay.
depending on what.
You would get better
Yeah.
structural.
It wouldn't make it solid.
We 3D printed a bottle and it was $180
Okay.
for my senior project.
3D print out of gold or something.
Yeah, right.
Okay.
I think
Depends on what you.
Either way, I think that'd be something to check, would be the price between 3D,
Absolutely.
3D printing it per gram and just buying like a solid sheet of acrylic of the right size and just cutting it down.
I don't think any expenditure that we have should be made just blindly without any.
Yeah, I think that goes for every subsystem.
In fact, we came up with a solution that we've got in the works. We're actually using a database to compare parts in the long term for us, just to not have to be able to recompile spreadsheets time and time again. But yeah.
As far as the temperatures, battery temperatures typically move pretty slow. Don't spend a whole lot of time and energy trying to get those temperature readings too much quicker. That's your time and energy is better spent. But what you have right now is sufficient. Don't try to make it faster, I guess is what I'm trying to say. If your battery temperatures are moving much faster than what you're reading right now, you have a bigger problem.
What would you say as a bare minimum? What would you be happy to see as a judge for sampling rate for those?
I mean,
We have about a second.
Yeah, yeah, that's typically what I would want to see. I mean, 5 seconds would probably be about the limit that I would want to see. At 5 seconds, you can start to see. 5 seconds gives you enough time to kind of predict a failure coming and shut the system down beforehand. 1 second gives you good, reliable data. You can actually watch what's happening, and that allows you to do like triage and troubleshoot, even if you don't have a failure. 5 seconds will stop a failure, but it won't give you the data you need to be able to understand it. 1 second will be enough to understand it.
Yeah, and they'll be, hopefully we've got that sorted out by come Lincoln, but I'm guessing that those are going to be one of those frustrating bugs that we're going to see when we've got the thing, up and running, knock on wood, like in the parking lot or something like that.
Right. So the nice thing about having it about 1 second is you can kind of do a little bit of error proofing just in the code, because if you miss something, you can just do a running average, and if you miss something, you can just go, okay, I'm going to ignore that point, and then and kind of move on. Especially if you're doing it on an Arduino, that allows you a lot more logic there. So, whereas if you're any slower than you have right now, you kind of lose the ability to do that. So, do you have have you guys done any calculations for pre-charge and like what time you're expecting your pre-charge circuit to take, and then for any of that yet?
Yep. With that, we did it, and then back in the summer, and kind of haven't looked at it since. We looked at the motor controllers. We're looking at the Reinhardt PM100DX, and they have their capacitance for the capacitors for the motor controller listed, and we found MATLAB code. Wisconsin actually distributed theirs as far as how to go about calculating if your resistor is known, how do you get your capacitor and whatnot for that, and it was basically just looked like a nice step input, and just the typical kind of RC rise time with that.
Okay.
95% was where we were trying to hit, and it was within 0.02 seconds.
Oh, that's real quick. Okay, perfect. I didn't see anything about a discharge circuit in the schematics. Did I miss it, or?
No, you didn't miss it. We have been playing around with that. That's not fully done yet. We're guessing that once you open the AARs, just have a switch on a path to the high volt ground to discharge those capacitors. But what would you say would be the best way to go about do?
I want to double check the rules on that. I don't remember if you're allowed to have logic in the discharge circuit or not. If it has to be one of those kind of always on type things where you just the current doesn't go through it. It's not the path of least resistance as long as your AIRs are closed. So let me double check the rules. I'll send you an email on that when you send me the presentation.
Yes, sir.
Everything else looked pretty good. The T-cell looked good. Are you using that logic for the battery box indicator light as well?
Well, we didn't use any. Roughly, the difference there is that the power source would be the DC-DC converter, 12 volts before the AIR. We didn't want to. It made more sense just as far as how we were organizing things in terms of safety to have the main T-cell light be powered off of the low volt battery, but because the LED is so tiny and we can, isolate it pretty well, we're thinking about powering that either directly off of the high volt pack or going off of the DC-DC, the 12 volt DC-DC converter, and then stepping down for whatever LED,
Right.
value, or whatever current we'd be looking to power that LED. But the same rough kind of logic, just the sampling point would be before the AIR as opposed to after the AIR.
Right. Okay. Other than that, I don't think I had any. I didn't catch anything else while we were going through it. I'd like to spend a little more time reading through it and looking stuff over, but I think you guys are on the right track here. So.
Thank you. I'll definitely get that sent out to you. I know it was a lot. It's been a lot for us, and I apologize. The documentation wasn't any higher quality than I learned this semester that CAD is an absolute must if you're going to do any kind of engineering work.
Yep.
So, yeah,
Yes, electrical engineers still use CAD, so.
yeah, that's, yeah, I didn't, you had to learn that the hard way.
Not a problem, not a problem at all.
And,
So, you know, when you're going through this stuff, if you guys have any problems, you know, feel free to reach out, shoot me an email. You know, I might not respond in an hour, but I'm typically pretty good about responding in a day. So.
Sounds good. That's better than I think most people here at the university. Yeah. So, yeah, I'll get this sent out to you later tonight, and yeah, thank you so much for your time. And was there any other?
Address the elephant in the room about registration.
Oh yeah.
Oh,
yeah,
so there's one more kind of oddball thing here. However, it's kind of a long topic. If you guys gotta go now, would it be possible to set up another time, or can we take like another 20 minutes to maybe address this?
Yeah.
I would lean towards setting up another time, but
Okay.
I'm open to what more or less you think.
I have to submit a midterm for my class, so I'm gonna have to bail. Sorry,
Yeah,
guys.
that's fine. I'm in the same boat. I have 2 tests tomorrow morning, so things are going well. But okay, yeah. So, let's see. Long story short, when we registered for Lincoln, we got on the wait list, but we accidentally registered for the combustion. So the idea might be to switch to combustion. Now it's just an idea. We haven't done anything like that we have to switch yet. But yeah, we'll schedule another time to maybe talk that over, because it seems interesting, but nothing is for certain, and everybody's got some interesting ideas. So but yeah, will this week later some night work?
Yeah, it sounds like you need to meet sooner rather than later if you're considering a change that large.
Well, the funny thing is that, you know, registration was last Wednesday, and we got the invoice, but we didn't pay it because we weren't sure, and they still haven't kicked us off because you're supposed to pay within 72 hours. So I don't know what's going on their end. Maybe they're confused too.
Have you talked to Martha and see if you can just switch it to electric?
Oh, that's fancy. Could I do that?
Just be like, hey, my bad. I messed up. I'm a first-year team. Please switch me to electric right now, Martha.
Hey, that would be pretty dope. Okay, yeah, I'm gonna email her. Is her email on the website, or am I gonna have to go through Collegiate SAE?
I can't remember.
Because I don't think I got her email from when I talked to her. Darn. Okay. If anything,
I'll see if I can find it. Since she met you at competition, I'm sure she would be fine.
Yeah.
I mean, that's her job, is to handle this, make sure everyone's signed up for the right thing. And if you're really struggling, I work with FSAE International every other week, so I could ask.
Yeah, that would be very
contact
helpful.
there.
Yeah, I'll see Kaylee in 2 weeks as well. So.
Oh
who runs
yeah.
The whole thing. So.
We'll make it happen.
Yeah.
Let you guys reach out. Do the initial work. If you run into roadblocks, let us know, and we'll see what we can move out of the way for you.
Yeah.
That will be very helpful, definitely. Yeah. Okay, cool. Well, yeah, I don't want to hold you guys here any longer. This was fantastic. We'll email you for another time, possibly this week. And yeah, thank you so much again. I think we've been doing a lot of phenomenal work. We're definitely learning a lot, and I can't wait to see us start building.
Same. Good job, guys.
Good job.
Thank you very much.
Thank you.
Have a great night. Thank you. Yeah.
All right.
Call and start crying.